In this video, I'll give you an introduction to meteorites. What are they? Where do they come from? And what can they tell us about the origin of our solar system? I'll give you a brief tour of the meteorite gallery here at the Natural History Museum of Denmark to show you some examples of important meteorites. Let me start out by telling you how the meteorites arrive here on Earth. I hope that you've already seen many shooting stars. Otherwise, do take some time to look at the sky next time you're in a dark place with a good view to the clear sky. Shooting stars are small pieces of solids that enter the Earth's atmosphere at high speeds. In the vast majority of cases, everything burns up in the atmosphere, but in rare cases, a small fraction may survive and fall in the form of a meteorite. A famous and very important example from Denmark is the fall of the tiny MARIBO meteorite in 2009. Here's a 3-gram piece of the little walnut-sized meteorite. The fireball that resulted in the meteorite was caught on a Swedish surveillance camera. This and some other data allowed us not only to find the meteorite, but also determine its orbit around the Sun before it hit the Earth. Finding the meteorite was not easy though. The size of the fall area was 100 square kilometers and the meteorite was only walnut-sized. Thanks to a very skilled German meteorite hunter, the search was successful, making MARIBO the 5th known meteorite from Denmark. The meteorite arrived in the atmosphere at a record high 29 kilometers per second. As it penetrated the atmosphere, its kinetic energy was transformed into heat, thus providing plenty of energy for the powerful fireball. Here's a picture of a 2-gram fragment of the meteorite. The surface is coated with a very thin fusion crust from the passage through the atmosphere. Since heating only lasted a few seconds, the material inside the meteorite remained cold and pristine, unchanged for 4.5 billion years. The particles that you can see here formed during the birth of our solar system, millions of years before the Earth formed. Also, although MARIBO is the smallest Danish meteorite, it is nevertheless by far the most interesting. It contains material that we have never seen before. A much bigger fall happened near Chelyabinsk in Siberia on February 15, 2013 at 9:20 in the morning. A piece of rock with a mass of about 12,000 tons entered the atmosphere at 18 kilometers per second. The kinetic energy of the object was equivalent to the explosive power of 500,000 tons of dynamite, or more than 30 times the Hiroshima bomb. It destroyed almost every single window in Chelyabinsk, and many people were hurt. Fortunately, no one died. I have a small piece of the meteorite here. The biggest piece was found at the bottom of a lake, below this large hole in the ice. Events like Chelyabinsk are quite rare. Statistically, we estimate that they occur about once per century. Incidentally, there was a somewhat similar event also in Siberia, almost exactly 100 years earlier, with an explosive power 5 to 10 times higher than Chelyabinsk. The TUNGUSKA event flattened more than 2,000 square kilometers of forest. As far as we know, no one was killed in this incident either. If you want to go hunting for meteorites, where should you search? Meteorites fall almost evenly all over our planet, but some places are easier to search for meteorites than others. Meteorites also survive longer on the ground in a dry area than in a wet climate. Therefore, hot and dry deserts are the best areas to search. This black rock in the picture is a meteorite. It's easy to spot, certainly a lot easier than finding meteorites in a cornfield like this. Cold deserts like Antarctica are actually even better because the flowing ice under certain conditions cause the meteorites to accumulate in certain areas, and because meteorites are easy to spot on the surface of the ice. In this picture, each flag marks a meteorite. We found 85 different meteorites within an area of about 100 square meters. In total, we found 942 meteorites during a 6-week season in Antarctica. The fall rate of meteorites is about 1 per 15,000 square kilometers per year, which makes about 4 per hour on the Earth as a whole. This may sound like a nice steady supply of these rare rocks, but unfortunately only very few of these will ever be found. In Denmark, the fall rate is 3 per year, but we have only found 3 during the last 3 centuries. The remaining 299 from the last century are still out there, so please keep your eyes open for meteorites at all times. So where do the meteorites come from? First and foremost, all meteorites found so far are from our own solar system. In fact, we're quite confident that if we were ever to come across a meteorite from a different solar system, we would be able to recognize its origin from outside the solar system immediately. So where in the solar system do they come from? Well, let's go back to the picture we looked at in the previous lecture. Primitive meteorites are samples of the dust and particles orbiting the sun when it formed. Most of this material was used to form planets, but a small fraction ended up in minor bodies, the so-called asteroids. Some of these asteroids never experienced any significant geological evolution. Therefore, the original particles and the dust never melted and have thus been preserved in these primitive bodies, documenting the earliest phases of our solar system. If you look at the surface of this asteroid, you can see a lot of craters on its surface. Each time such a crater forms, pieces are knocked off the surface of the asteroid and sent into free orbit around the sun. After a few to several million years, such a fragment may fall on Earth in the form of a meteorite, such as the one I'm holding here. If we cut a slice through this meteorite, we can see and study the original particles that formed in the disk around the young sun. We'll get back to these particles shortly, but let me first show you some of the other very different types of meteorites that we find. I just told you that many of these asteroids never experienced any significant geological evolution. They just remained primitive dust balls sampling the earliest materials in the solar system. But some of these bodies actually did melt, first and foremost because of a radioactive isotope known as aluminum-26. Decay of this isotope caused these asteroids to melt. The metal they contained drained down to form a central core. Some of the silicates or stony materials also melted and was squeezed up on the surface where they created volcanic activity. So therefore, these asteroids have a cross-section that really resembles something very familiar, our own Earth. In the center of the Earth, we have a metal core. Outside that, a mantle and a crust, which is the one we're standing on here. These asteroids subsequently cooled and crystallized and collided with other asteroids. And fragments of such a broken or destroyed asteroid provide us with iron meteorites from the central metallic core, stony ions from the interface between metal and silicate, such as this one, and stony meteorites or achondrites from the surface of the asteroid. I've summarized the evolution of asteroids in this figure. Some asteroids remain primitive dust balls. Those are the sources of primitive chondrites. Other asteroids melted, differentiated into core, mantle, and crust. And fragments from differentiated asteroids have provided us with iron meteorite, stony ions, and the so-called achondrites from the crust. In total, we estimate that we have meteorites from at least 100 different asteroids. Most of the asteroids we have sampled came from differentiated asteroids. But interestingly enough, most of the meteorites that fall on Earth seem to come from relatively few primitive, unmelted asteroids. Statistically, 95% of the meteorites falling on Earth are from the 15 known chondrite parent bodies, whereas the last 5% come from approximately 100 different differentiated asteroids. Let me get back to the primitive meteorites and show you what they look like and what they can tell us. If we look at a hand sample, we can see that about 50% of the surface of this chondrite is covered by fusion crust. Under the fusion crust, we can see the most interesting part of the meteorite, well-preserved samples of the material that formed during the birth of the solar system. If we look at a slice cut through a similar meteorite, like this one, we can see that it's composed of different types of particles embedded in a fine-grained matrix. These small round objects that you see here are the chondrules that I introduced to you in the previous video. Note that you do not have to look hard to spot chondrules. They are everywhere. It's a main component in this meteorite. By preparing thin sections of the meteorites, we can study the chondrules in great detail. Here's a picture of a 1 millimeter chondrule. What we've learned is that these round objects formed from flash heating of a pre-existing dust precursor. We find them in a wide range of sizes. Diameters from 0.01 millimeter to 1 centimeter are not uncommon. The most common minerals are olivine and pyroxene, two types of minerals that are also very common here on Earth. We also find iron, nickel, metal, and often we can see that the melt did not have time to form crystals when the chondrule cooled in space. The space between these crystals are therefore filled with glass. No matter which property we measure, the chondrules turn out to be highly diverse, and the textures is no exception. Here's a selection of chondrule textures that we have observed. These textures can be reproduced in the lab when we do the experiments under conditions similar to those that the real chondrules experienced during the birth of our solar system. Chondrules are therefore probes of the conditions that existed during the first phases of the solar system. Chondrules also contain radioactive isotopes that allow us to date them using a machine at the basement of this building. And what we find is that the most chondrule formed during the first few million years after the birth of the solar system. If we look at the slides again, we can see that there are also some irregular particles like this one. This is an example of a CEI, a calcium aluminum rich inclusion. Unlike the chondrule, which formed as melt droplets, this irregular inclusion condensed out of a very hot gas. This is an example of such a fine-grained irregular CEI. Some of the CEIs were remelted, thus ended up looking a bit like the chondrules, round and more coarse-grained than the original condensate. Since calcium and aluminum are the main elements in CEIs, they are composed of minerals that are rich in these two elements. As I've shown you, we can learn a lot about the birth of our solar system by studying the details of the primitive meteorites. But there's much more to be learned. Far from all the clues can be seen with the naked eye. Here at the Center for Star and Planet Formation, we also study isotopic compositions of the elements in the various components of the meteorites. Many of the isotopes are radioactive, and we divide them into two groups: the long-lived, that decay so slowly that they are still present today in the meteorites. In contrast, the short-lived are now extinct, but have left traces in the form of the elements they decayed to. So here's a list of the short-lived isotopes that we study. But why is it of interest if these isotopes are no longer present? In fact, there are several reasons to have a detailed look at these isotopes. The fact that they were present in the early solar system already provide important clues. Since they are short-lived, they must have formed shortly before the solar system formed, otherwise they wouldn't be there. Some of the short-lived isotopes are only formed in supernova explosions. Other isotopes form in other types of stars, and some could have formed within the solar system by particle irradiation from the young sun. In other words, their presence tells us something about the surroundings in which the solar system formed. Studying the abundance of short-lived isotopes in the meteorites provide information of the stars that contributed matter to the solar system. By comparing areas in our galaxy with active star formation, we may be able to find young solar systems formed under conditions similar to our own. Another interesting aspect of short-lived isotopes is that they may, on a certain condition, be used as chronometers that provide us with high-resolution chronological information about the early solar system. And finally, the rapid decay of short-lived isotopes also provided the early formed asteroids with a powerful heat source. Decay of aluminum-26 resulted in the melting of some asteroids, and as a result provided us with the differentiated meteorites such as the iron meteorites. By far, most meteorites come from asteroids, but there are two important exceptions: meteorites from the Moon and Mars. In the next video, I will talk more about Mars and why we think that we have meteorites from our neighboring planet. But let me just give you an introduction to whet your appetite. All Martian meteorites are volcanic rocks. There are 4 different types of Martian meteorites, and one of the Martian meteorites is unique. It's named Allen Hills 84001 because it was found in Allen Hills, Antarctica in 1984. It's the oldest known rock from Mars. It's porous, and Martian groundwater has circulated through it. Since we know that bacteria thrive under similar conditions in volcanic rocks on the Earth, a search for evidence of life was conducted in this meteorite. A famous paper from 1996 reported possible evidence, including these worm-like structures that resemble fossil bacteria. The meteorite has been studied by a large number of research groups since then, and the consensus is that the structure is formed by abiotic processes. That obviously does not rule out life on Mars. The search for life on Mars is still ongoing, but so far we have not found a smoking gun. In the next video, we will look deeper into the potential for life on Mars and its possible implications for life on our own planet. There's one more body in the solar system where we have meteorites from, the Moon. You can see some of the meteorites here. Given the proximity of the moon, it would seem logic if the majority of meteorites came from our moon, but that is far from being the case. Lunar meteorites are surprisingly rare. It seems that large impacts on the moon result in intense, but brief, showers of lunar meteorites on the Earth. The observation that lunar falls are rare at the moment thus suggests that it has been a while since the last big impact on the moon. The moon is the only object in the solar system from which we have meteorites, and samples returned through missions. The Russian and US missions sampled 7 different locations on the near side of the moon. The lunar meteorites, on the other hand, probably sampled the far and near side quite evenly. The combined evidence from all these samples have allowed us to piece together how our moon formed. As it turned out, it has a very unusual and somewhat dramatic story that I'll get back to in the next video. So let me finish off by reminding you what I just told you. Meteorites are rocks from our own solar system that have landed on the Earth. Most meteorites come from a diverse group of asteroids. The most primitive asteroids have seen virtually no geological activity since they formed 4.5 billion years ago. At the other extreme, we've sampled asteroids that melted completely shortly after the solar system formed. Studies of meteorites have helped us reconstruct when and how the solar system formed, and it has allowed us to learn something about the surroundings in which it formed. We also have meteorites from the Moon and Mars. And since the Origins course focuses on the evolution of life on our own planet, the possibility that it also formed and possibly still exists on Mars is obviously of great significance. We've learned that pieces of Mars fall on the Earth and that there could be primitive life on Mars. So before you listen to the next video, take a moment to think about the possibility that life could spread from one planet to another within our and other solar systems. Do you think that could be possible?